In the vast expanse of applied physics, there exists a comprehensive and profound discipline known as continuum mechanics, a realm that transcends the discrete and delves into the seamless study of materials and substances as continuous entities. This intricate tapestry intertwines principles from classical physics with a continuum approach, providing a framework to understand the behaviors of matter on both macroscopic and microscopic scales. The continuous fabric. At the core of continuum mechanics lies the conceptual fabric of materials as continuous substances. Unlike the discrete realm of particle physics, this discipline treats matter as a continuum, seamlessly flowing and interconnected. It unfolds a narrative that spans from the macroscopic dimensions of bridges and buildings to the microscopic interactions between atoms and molecules. Deformation and strain. Continuum mechanics weaves its threads through the exploration of deformation and strain, concepts that capture the response of materials to external forces. Whether it's the stretching of rubber, the bending of beams, or the compression of solids, the discipline quantifies the intricate deformations that materials undergo. Stress and equilibrium. The discipline unfurls its chapters through the understanding of stress, the internal forces that materials experience. Continuum mechanics embraces the equilibrium equations, which dictate that materials respond to external loads in a manner that maintains balance, ensuring the stability and integrity of structures under various conditions. Constitutive equations. In the continuum realm, materials possess inherent properties that govern their behavior. Continuum mechanics introduces constitutive equations, which encapsulate the relationship between stress and strain. These equations become the poetic expressions of material characteristics, allowing engineers and scientists to predict how materials will respond to different conditions. Fluid mechanics. As the narrative flows, continuum mechanics extends its reach to the fluid realm. Fluid mechanics within the continuum perspective treats liquids and gases as continuous media. It explores the flow of fluids, from the gentle meandering of rivers to the turbulent currents within pipelines, unraveling the dynamics of fluid motion. Elasticity and plasticity. Materials, in the continuum view, exhibit elastic and plastic behaviors. Elasticity, a property allowing materials to return to their original shape after deformation, becomes a key protagonist. On the other hand, plasticity unveils the irreversible deformations, marking the permanent changes that materials undergo under certain conditions. Tensorial nature. Continuum mechanics introduces the tensorial nature of physical quantities, transcending the simplicity of scalar and vector representations. Stress, strain, and other properties become tensors, allowing for a more nuanced and comprehensive description of material behaviors in multiple directions. Thermodynamics and continuum. In the thermodynamic realm, continuum mechanics becomes a companion, exploring the coupling between mechanics and energy. The discipline embraces the laws of thermodynamics, incorporating heat transfer and energy considerations into the continuum framework, revealing the thermomechanical intricacies of materials. Applications in engineering. Continuum mechanics finds practical application in engineering marvels, from the design of structural elements to the optimization of manufacturing processes. It provides the language to describe, analyze, and predict the behavior of materials under diverse conditions, offering engineers the tools to create robust and efficient systems. Computational continuum mechanics. In the age of computational prowess, continuum mechanics seamlessly integrates with numerical simulations. Computational continuum mechanics allows scientists and engineers to model complex material behaviors, predict structural responses, and simulate a myriad of scenarios, opening new frontiers in materials research and design. In essence, continuum mechanics is the profound tapestry that unravels the continuous nature of materials, providing a unified framework for understanding the mechanical behaviors that govern our physical world. It is the bridge between the macroscopic and microscopic realms, offering a lens through which we can explore and engineer the materials that shape our technological landscape.